Hey class, welcome back. In this section, we're going to take a look at steps for calculating probabilities when we're dealing with the sampling distribution of X bar. So the idea here is that instead of talking about what proportion of the population has, say, marks greater than 70, if you think back to our marks example, or another way of saying that would be if I randomly chose one person, what's the probability that he or she would have a mark greater than, say, 70? That's what we did in Unit N. But here what we're doing is we're saying, what if we took a sample of, say, 16 people and averaged them out, averaged their marks out, and came up with an X bar? What is the probability of getting a sample mean greater than 70? Okay, so, or in our case, I think I've got 70 or less. So let's take a look at that. It would be a really good thing to go back and listen to that first video on Unit E, because that talks about why we're doing this and the importance of the central limit theorem and the first limit theorem. But I'm going to assume that you've done that, so let's talk about steps for calculating probabilities. So we're going to use the same 6 steps introduced in the last unit, that is Unit N. And only steps 1 and 3 are going to be a little different, and let me show you how that works. So let's recall the stats marks example. Suppose the distribution of exam marks for all Alberta stats students is normally distributed with a mean of 60, so that's our mu, and a standard deviation of 12. Now, in this particular one, I'm not talking about just a class of 50 because I want quite a large population here. You'll see why when we take a look at something called the finite population correction factor next. So think of all stats students here then. What is the probability that a randomly chosen sample of 16 students, so that's a little n of 16, will yield a mean of 70 or less? What's the probability of getting an X bar of 70 or less? So let's walk through the 6 steps, and you'll see that they're really similar to what we did in Unit N here. So the first step, need to get to the right page here, is to determine the characteristics of the population, including the type of distribution. So what we've got here then is that X is normally distributed with a mean equal to 60 and a standard deviation equal to 12. What that means, according to the first limit theorem, is that the X bars will also be normally distributed with a mean equal to 60 and a standard deviation equal to sigma over the root of n. So sigma over the root of n will be 12 over the square root of 16. And that's our n, right? Is 16. So that's 3. So I could just put a 3 in there, but I'm just going to leave it as 12 over the square root of 16. Draw a picture representing the probability to be determined. So let me draw a distribution here, like that. And this then is centered on 60. We're taking a look at the distribution of all possible X bars. And we're going to take a look then at what is this probability here from 70 down, like that. And so the probability then is just this guy right here. What's the probability of getting an X bar of 70 or down? Remember, with a normal distribution, it doesn't matter whether it's less than or equal to, because it's a continuous distribution, not like the binomial distribution. Standardize X. So the only difference here is that instead of having X minus mu, we have X bar minus mu, and then instead of sigma, we have sigma over the root of n. So that's the difference here when we're dealing with a sample. In our particular case, we have 70 minus 60 over 12 divided by the square root of 3, and that comes to 3.33. Right there. So now we're just into the rest of our regular steps for a normal distribution. Let's draw a normal distribution here. Whoops, that's not very good. Let's try that again. Now, this is actually quite a tight distribution of x bars here. The original distribution is much wider, but remember the standard deviation of this is actually 3. 12 divided by the square root of 16, which is 3, not the original 12. But it's still centered on 60 up here. And when we standardize this into a z, it will be centered on 0 with a standard deviation of 1, just like any z value. So this 3.33 then corresponds to a 3.33 here. And we're looking at all this area here, all the way down. Now, the reason why I hatched it that way is, remember that the table will give us this area here, and then we'll add on another 50% here. If you were to go back to the cases thing, this is just a case 1. And so case 1 says the probability that you get a z less than some value, 3.33, is equal to 0.5 plus the table value for 3.33. Let's go back to the table. Right there. Oops. That took me to the wrong spot. There we go. Okay. 3.33. Remember what these numbers mean is the number of standard deviations away from the mean. And so 3.33 is way, way out here in the tail. 3.3, oh, that's interesting that they're, I wonder what happened to the 3.33. Anyways, it's right in here, so it's about right in here. So it's 0.4995, let's say. I wonder what happened to that line there. Must have disappeared there. Should be a 3.33, so that's just an error that we have here. So we'll just have to kind of interpolate there. It's actually 0.4996. So let's go back to where we were. And so this then is 0.4996. And so that's going to be 0.5 plus 0.4996 is 0.9996. It's almost 100%. So what we're saying is that there's almost 100% chance that if you took a sample of 16 people and averaged their marks, that there's almost 100% chance that they would get an average of 70 or less. All right, almost no chance it would be above 70. So that's how that works there. All right, let's work through the next one here. The next one here says, actually, I might just leave that one for homework for you. So what's the probability that a sample of 16 marks will yield an average between 57 and 63? So I'm going to leave that for you, as well as this one here. Actually, let's take a look at that one. What's the lowest average that we can expect to obtain in a sample of 16? You know what that's all about is, remember those empirical rules at the end of Unit C, where we said that if you go mu plus or minus 3 standard deviation, that should be about 99.7% of the distribution. Well, in our particular case, the mean of the x bars is still mu, And we're talking about the lowest average, so it's not plus or minus, it's just minus 3 times sigma over the root of n, because we're talking about the distribution of sample means. So that's going to be 60 minus 3 times 12 over the square root of 16, and that comes to 51. So that is about the lowest average that we can expect. Let's take a look at the next one down here. And it says, suppose the distribution of monthly phone bills in Red Deer is normal, with a mean equal to 280 and a standard deviation equal to 40. So there's your mu and your sigma. What's the probability that a sample, that's your n of 36, will yield an average, so a sample average is an x bar, of 270 or less? So that's going to be x is normally distributed with a mean of, where was that again, 280, standard deviation of 40, and we are looking for the probability that x bar is less than or equal to 270. I'm going to leave it there, and you can finish that up. But I'm going to start you on this next one here, which will also be done for homework. Find the smallest interval that contains 99% of sample means. That's kind of goofy when you think about what does that mean. That's actually going to help us when we get into probability distributions with confidence intervals. This is how the thing works. So we're talking about a mean here of 280, and we want to find two values that have 99% of the distribution between them. Now, the smallest interval would be the middle 99%. Think of it this way. Suppose I said, what's the smallest distance between two numbers that has 50% of the distribution? Well, if you take a look at any half of a normal distribution, theoretically it starts from the mean and goes to infinity. So that's the largest possible interval. But the smallest would be the middle 50%, so 25% on either side, where in a normal distribution the numbers are kind of bunched up at the middle, right? They form that bell curve. It's the same idea here with 99%. So 99% would mean that you've got here half of 99%. So that'd be 49.495 there and 0.495 here. And that would leave you with 0.005 there, or 0.5%, and 0.005 there. So you want to find out what are those two values. Let's call them x bar 1 and x bar 2. And see if you can figure out what those are. Now, I haven't actually given us a lot of space here, so we're going to have to fill in some spots there. Anyways, I'm going to leave that one for homework, and I would like to leave it at this point.